Hello students, so welcome to this class. In this class we'll try to cover today T10 mode, as well as we'll try to derive the field components for the TM mode. Fine. So in our last class we saw that the field component associated with the TE mode in a rectangular waveguide. Okay, so here we are going to learn the T10 mode. Actually, we are going to explore the T10 mode because in practical system we are using very frequently this mode. So let us discuss this first, and after that we'll be exploring the field components for the TM mode. Fine. So this is a rectangular mode. Fine. So the purpose is very clear here, why we are starting once again the TE mode and particularly T10 mode. The reason is actually because most of the practical system you will find that the users are exciting this T10 mode. Okay, the one of the convenient thing with the T10 mode is that is the field component. Okay, so easily you can couple the waveguide, okay, to get this mode. Fine. So I will be showing all the field components and how to excite and how to recognize this is T10 mode or T20 mode. We'll be discussing all those things, okay, in this class. Fine. So let me recall first the mode we studied in the last class. Okay, so yes, so I believe you remember the last class. So for T mode particularly, okay, so just a minute. So these all are the modes for the T mode. Fine. And how many field components? There are 5 field components for this T mode. Okay, now the thing is, if you see clearly, because we are much interested about this dominant mode. Okay, so TE10 means here M is equal 1 and N is equal 0. Fine. Now let us figure it out that how many field component will exist for TE10 mode. Fine. So if you see the first one, which is HZ, okay, this field component, you will find that the moment you are putting M is equal to 1, okay, that is fine. Here it will be 1. Fine. So it means it will carry AMN cos pi x by a e to the power j beta z. Similarly, if you see the EX component, okay, you will find the moment you are putting N is equal to 0 here, okay, here, so the whole component will 0. It means this is 0. Fine. Similarly, if you see here EY component, you will find that this is a cos and this is N and N is 0, so this will be 1. But here, okay, this is 1 actually, and when you see this EY, you will only get the sign component only. Fine. Similarly, if you see HX, so you will find this component will also be there, because this cos n pi by b, so cos 0 will be 0. And here if you see this HY component, so you will find that here this is complete 0, so this component will also 0 here. So it means that we left with the 3 components. One is HX, HZ, EY, sorry, just a minute. Yes, so we left with EY and HX. Okay, so basically we have HZ, EY and HX component. So let us rewrite down, okay, these components, and we'll see. Fine. So I'm writing once again all these modes here. Fine. So dominant mode TE10, a very special mode. Fine. So the hz component will be a10 cos pi x over a e to the power j beta z. Fine. Another component will be hx, which is j beta a by pi a10, and of course sine pi x by a e to the power j beta z. And the last component will be ey component, which is minus j omega mu a divided by pi a10, and here this is sine pi x over a e to the power minus j beta z. Okay, so right now we have three components, and here you can see there is a one electric field component, another two magnetic field component, which is one is in a transverse direction, other is in the longitudinal direction. Fine. Now here if you see actually the ey, you will find that this is a sine function. Fine. And this kind of function we can easily couple in a waveguide. I'll show you how. Fine. But before that can you find it out or can you guess some application of this TE10 mode? So basically, like if you see this picture, so this is actually microwave bench. Okay, this is what? This is microwave bench. So you will see this microwave bench in a microwave lab, and this is a very basic instrument, you know. So you will find the number of components are there. Okay, so I can mark in a picture. So here you can find this is a source, basically gun or the klystron based, and here you have VSWR meter here. Fine. And you can see here you are exciting or you are coupling actually the power from this point, correct, and you are collecting here. Fine. In between that you will find that there is a waveguide. This is the waveguide actually. Okay, can you find it out? This is the waveguide. This is the waveguide. All are this up to here. This is the X band waveguide. Fine. And basically here you will find that we are exciting the TE10 mode, correct. In between that you will find that there are number of components. Okay, like this is the isolator. Fine. This is attenuator. Okay, this is frequency meter, and this is the slotted line. Fine. So basically, like if you want to explore this bench, okay, so you will see that here particularly the slotted line, there is a probe is there actually. So you can by rotating this knob actually you can change the position, and that is how you can find the maxima and minima on the waveguide. And depending on that actually maximum minima you can find it out the guided wavelength, then after VSWR and all the things. Fine. So the purpose of recalling this microwave bench is that because this all the things, okay, we are operating at the TE10 mode. Okay, the reason is that because this field component, if you see, is very actually easy to understand. Okay, these functions, this ey is a function of sine, hx is function of sine, and sc is a function of cos. Fine. So yes, we can plot these fields on the waveguide. Okay, and we can find it out the distribution of the field of electric and magnetic field, followed by we can also find the surface current. Okay, we have hz and hx. Definitely this could be utilized to find the surface current. Okay, like this. Okay, hopefully you know this relation, J is equal to n cap cross h, and in this way the surface current could also be estimated. Fine. Now let us see that how this mode will look like, or how you will see this mode in a waveguide in a different cross sections. Okay, so yes, So before this thing, I think I should copy these things, and I can copy all these components. Hopefully this is visible to you. Fine. Now here if you see, this is the field pattern for the TE10 mode in rectangular waveguide system. Okay, so you can see the first picture here. So the red one is here, the electric field, and the blue one is representing the blue lines representing the magnetic field. Now this is what actually, this is the cross section, means XY. Okay, remember the waveguide, okay, how we drawn last time. This is the waveguide. So I'm talking about this cross section. Fine. So this cross section you can see here, and you will find the field patterns, and basically if you see in a y direction, okay, in a y direction, this is a x and this is y, correct? So changing the position, okay, along the y, okay, and plotting the ey component here, so you will experience there is a field variation of like a sign. You see here, this is a sign variation. You can easily identify this thing, correct? So here at the middle this is maxima, and at the edges this is 0. Fine. This is what the sine function is. Fine. So if you are putting these things, x is equal 0, it will be 0. Okay, and in the mid actually you have the maximum these things. Similarly, you can find the hx, okay, because in z direction the propagation is happening. Fine. In if you see hx, actually this is again the sine function. Fine. Okay, and it like if you see in a cross section, you will find that actually the lines are horizontal lines of the blue lines. Fine. Now the thing is, if you see on the top, okay, fine, if you like here this second picture, if you see, okay, this is the complete sorry, this is at the yz plane. Okay, so at yz plane, what you will see actually, this is the electric field we plotted here. Okay, and there is a sign distribution, clearly you can see. Now talking about this magnetic field, actually if you see on the top, okay, fine, on xg plane you will find the loop like that, and the wave is propagating in a z direction. Okay, hopefully these functions are clear to you. Okay, now in an easy way, like how to identify these modes, it is sometimes very important. However, we are mainly focusing here the TE10 mode. Okay, so here you can find this this is a TE10 mode. Fine. And you will see these are the vertical lines, okay, is representing here the electric field, and the horizontal lines are representing here the magnetic field. Fine. So like if you move along along the x direction, so you will find the experience in x direction only, correct? So that is why you have 1, okay, or like a 1/2 variation. You can see here, this is a half variation, you can find it out. Okay, half variation, so we're representing as 1. And if you are moving in along the y direction, okay, if you are walking on these lines, actually you will never experience anything. Fine. So this is 0. Fine. This is another situation when we have the waveguide such that dimensions has a is greater than b. Fine. So in that way, this will be somewhat flipped to the T01 mode. Now this is quite interesting, like when we how we can visualize this TE20 mode. Fine. So it means that there will, when we are moving along the x direction, you should get at least two variation. This two stand for the two half wavelength variation. Okay, like you can make some observation like that. Fine. Okay, so here you will find a maxima here and maxima here. So there will be two sign, you can see here like this. Fine, two half sign variations, correct, and that is why this is 2 0. And along again, if you move to y direction, you will find that there is a no variation, that is why this is 0. Fine. So hopefully, like changing the variation, particularly we focused the mode like TE and 0. So like 3 0, 4 0 and 5 0, like that. Okay, and the reason is that why we are exploring this thing, because the part of the coupling, because in a microwave it is somewhat very quite challenging when we are going to excite some higher order modes. Fine. Okay, so this is the field pattern of the TE10 mode. Hopefully this is clear to all. And basically these fields, you can carry these things in a MATLAB and you can plot and you can verify once again. Fine. Now coming over once again, this 3D view is quite interesting. So you will find that this is a y, okay, this is x, and the wave is moving along the z direction. Fine. So here you will find the red color is the electric field. So you will find that maximum at the center, means it is, we are expecting a sine, half sine variation, okay, on the cross section of xy. Fine. Okay, now in a if you see from the previous this thing equation, you will find the magnetic field current, magnetic fields actually, and this is in a loop. You can find this thing, this is in a loop. Fine. So this is one of the representation actually showing the magnetic and electric field. Now another is the current actually. Okay, so this dark one, okay, the dark this dark one, this is the current actually. Fine. So yes, you can estimate this current with this, like this relation. Okay, so once you know the magnetic field, okay, components, you can estimate the current as well. Fine. So this is all about for the TE10 mode. Fine. And hopefully you can visualize some of the part. So basically in a cross section, okay, you will finding a sine wave like this, because this is a sine function. Yes. Okay, now the thing is another point is that on the top actually you will find a loop of the magnetic field like this, correct. So how to excite these kind of modes, okay, in a waveguide. So like if you can recall, or if you can remember a very basic thing, a wire carrying a sinusoidal current, okay, or a high frequency signal actually. So what will happen, the current will flow along the length, okay, let's say it's going in a z direction. Fine. In a z direction it is going, the current is going in a z direction, and the magnetic field will be carrying in a loop, okay, like that in xy plane. Hopefully this fact is clear to you. Now considering this fact, we can find the way of exciting or coupling this TE10 mode. Okay, fine. It is because in a microwave engineering we supposed to interact this mode. So this is actually the way by which you can excite. This is a probe, okay, this is a probe you are inserting somewhere here, okay, and it will be a magnetic field like this, okay, and the electric field like this. I can draw the electric field like this, okay. So on the cross section of xy, okay, you will be having, and this is actually at the middle. So you can find, like if you see from the cross section xy, okay, so this is the probe, and here this is maximum, and the electric field will be like this. Fine. So we are trying to make actually the half wave sign variation in a xy, as well as if you see the top of that, from the top of this actually, so you will find this magnetic field will be in a loop, okay, and this is actually propagating in a z direction. Okay, so hopefully this is clear, and like I can show you in a practical scenario that how the things are happening. So I shown this thing, this microwave bench. So you will find that there is a probe actually, okay, from the klystron power supply, and this things or gun, this thing we are exciting like this. So there is a vertical pin, okay, here you can find there is a vertical pin, and from there actually we are trying to make the similar situation for the TE10 mode what the component has actually. Fine. Okay, so hopefully this is clear to everyone, and yes, we can discuss after the class also, okay, if you have any doubt on it now. Okay, so let us move to the TM modes. Okay, we're supposed to explore the TM mode also. So TM modes for rectangular waveguide. Fine. So will not take much time because we already explored in detail the TE mode in earlier classes, these things. Now we'll be directly recalling the second order partial differential equation, and we aware here this for the TEM mode, okay, the longitudinal component will exist here is Ez. Fine. So let us write down, okay, the equation once again here. So this is tau square Ez xy, okay, dou x square plus dou square Ez xy over dou y square plus kc square Ez x comma y is equal to 0. So once you estimate your Ez, okay, you can estimate other transverse component as we did actually in the TE mode in a rectangular waveguide. Fine, because we saw in a previous class that this transverse phase component, okay, we can write down in terms of the longitudinal component, which is Ez. Fine. So now again we will be using the same technique here, okay, solving these things definitely by separation of variables, okay, and we supposed to assume here the solution will be existing in this form, x of x and capital Y of small y. Fine, in a same sense. Now if we are using this in above equation, yes, you can write the two different equation like this, okay, which is this plus kx square x is equal 0, d square y dy square plus ky square y of y is equal 0, and of course kc square is kx square plus ky square. Fine. Okay, so these differential equation, now if you see, this depends on the single variable of x. Fine. Now writing the solution is quite easy. Once again, what we saw previously, so we can write the solution for these two differential equation as a sin kx x, b cos kx x y C sine ky y plus d cos ky y. Fine. Now once we know the solutions, actually, yes, we can write the longitudinal component as EZ is a function of xy is x of x and capital Y of y. Fine. So okay, let me just copy this equation. So this is 1. Okay, it's quite easy with this writing the equations, and this is 1 into this one, the second one, which is a y for y. Oh, not fit, unable to fit, sorry. Okay, fine. Hopefully the message is clear what I'm doing here. So I'm multiplying this a sine kx x b cos kx x, okay, and the second one, which is c sine ky y d cos ky y. Fine. Okay, so this is actually the resulting longitudinal electric field. Fine. And similarly you can write down the overall field but just by multiplying e to the power j beta z. Fine. So once you have this easy component, we know that how to write the other components. Means I'm talking about the ex, ey, hx and hy. These are the transverse component moving towards the z direction. Fine, in a direction of the propagation. So we saw in our previous classes how we related this easy component with the different ex, ey and hx component. Okay, so hopefully you can recall those things. I'm writing here the final field components. Okay, so then after we'll be discussing those things. So okay, so I can take the new page. So the complete field components will be here. Ex, the function of x, y, z is, just a minute. Okay, so this is j beta by kc square and dou Ez over dou x. Fine. So if you are solving this, you will be getting j beta m pi by kc square a bmn before that, I think, okay, yeah, just let me recall the boundary condition. I think I should write the boundary condition, then I'll jump over here. Okay, sorry for this. So okay, so okay, so first of all, writing this easy component, which is xyz, the overall easy component. So just multiplying with e to the power j beta z with in the last equation, sine kx x. It will be big jump if I'm writing the ex, ey, hx and hy whole thing. Okay, sorry for that. Cos kx x c sine kyy plus d cos kyy, and of course e to the power j beta z. Fine. Now in a similar way, we'll be imposing the boundary condition here depending upon this geometry we took, okay, on the horizontal walls and the vertical walls. Fine. So writing the components here, okay, so the tangential component will be 0. So ex x 0 z is equal to Ex, X, B and Z is equal 0. So this is what? This is actually the Ex component. Okay, that Ex tangential component on the horizontal walls actually will be 0. Fine. So this is for the horizontal wall. Horizontal walls. Fine. Another thing is that EZ component. Okay, at the same location means X0Z and EZ XBZ is equal to 0. This is again on the horizontal walls. Fine. Now, recalling the EY component on the vertical walls like this 0, Y, Z. Okay. And EY A, Y, Z means at the right hand side vertical wall. Fine. And this is left one, this is right one. Okay. Fine. Similarly, here you can see this is a bottom one, this is a top one. Now, EZ component once again on the vertical walls like 0, Y, Z and EY A, Y, Z again will be 0. So these are all the tangential component. Fine. Definitely this should be 0. Okay. Now utilizing this boundary condition, okay, here you can write down certain things, correct, as we did in a previous class. Okay. So yes, so starting from the EZ is 0, Y and Z, correct, is equal to 0. So what it will give? So EZ, okay, putting X is equal 0. So putting X is equal to 0, if you see this will be 0. Fine. And the rest of the component is a function of Y only. Okay, so leave it. Now here if you see, this is B Kx X again. So if you are putting 0 here, so this component will be 1. Fine. It means this is going to be non-zero quantity, but this has to be 0, means EZ component has to be 0. It means that forcefully, correct, we supposed to take B is equal 0. One thing. Another is that when EZ AYZ is equal 0. Okay. So here B is equal 0. Forget about these things. Okay. So now, yes. So in place of X, you are putting A. So this is Kx. So this is Kx A is equal to M pi. Fine. Okay. This should be 0. That is then only actually we can say this EZ component will be 0. So this is one thing. In a similar sense, actually you can apply once again EZ at X 0 and Z is equal 0. So this will give you D is equal 0, and when you apply the boundary condition as X B Z, okay, is 0, so this will give you the KYB is N pi. It's the same kind of things what we got in a last time for the TE mode. Okay, so here basically this Kx and Ky are identical, okay, for these things for the TE mode. Fine. And yes, so here we have a B is equal 0 and D is equal 0. It means we left with A and C. Fine. So we can say a combined constant for this. Let us call as BMN. Fine. So with this actually I can rewrite the longitudinal component EZ as BMN, fine, sine M pi X over A sine N pi Y over B, and of course e to the power j beta z. Fine. Now you have to use actually these this field component, longitudinal field component of EZ, to estimate the rest of the transverse component named as Ex, Ey, Hx and Hy. Okay, now so Ex will be, if you write down, this is minus j beta. So I'm not writing all the time x, y, z, this function. It is understood Ex is a function of Ex, x, y and z space completely. Fine. J beta over kc square dou Ez over dou x. So if you solve this, you will get minus j beta m pi over kc square a bmn cos. Okay, please differentiate and try to match this equation. Sine n pi y over b e to the power j beta z. Fine. In a similar sense, you can estimate Ey also as minus j beta over kc square dou Ez over, this time differentiating with respect to y, and it will give you j beta n pi divided by kc square b bmn, and here sine m pi x over a cos n pi y e to the power j beta z. Now we left with two more component, which is hx is j omega epsilon over kc square, and this is dou Ez over dou y is equal to j omega epsilon n pi over kc square b bmn, and yes, I think copy. It is somewhat very tiring. I can copy this thing. Okay it's easy here. Okay, fine. Okay, so this is hx component. Fine. So this facility you cannot get while writing on a board. Fine, I can get here. So now the last one is hy minus j omega epsilon over kc square dou Ez over dou x. Okay, that's supposed to be differentiated with respect to x, and yes, you have j omega epsilon m pi. Yes, I'm writing in a correct way, kc square a, and again bmn, and there we may cos m pi x by a, and I think sine n pi by b. Okay, so I think I can copy this one. Fine. Yes. Okay, so right now we estimated all 5 component associated with the TM mode, imposing the proper boundary condition of rectangular waveguide. Hopefully this is clear to all. It is a very straight line. Now the rest of the parameter I believe I can write, or you can estimate like what we did previously, because again and again we are repeating the same thing. So yes, so we supposed to once again recall like phase constant, cutoff wave number, cutoff frequency, guide wavelength, and what else it was, cutoff guide wavelength. Yes, cutoff guide wavelength for the TM mode. Fine. So right now we are now talking about the TMN mode. Fine. Okay, so let me write down here these things. First, beta mn is this k square minus m pi by a whole square n pi by b whole square. So yes, you can estimate like this, k times of 1 minus fcmn cutoff frequency So again we'll be writing all the things in terms of the cutoff frequencies like what we did in the last time. KCMN we may write like this: 2 pi FCMN under root mu epsilon, and the cutoff frequency formula is once again is same, which is 1 upon 2 under root mu epsilon under root m pi by a to the whole square plus n by b to the whole square. What else? We left with lambda g guided wavelength mn is 2 pi by beta m n. So yes, you can write like this: 1 minus fc over f to the whole square. Fine. So this is what the phase constant, cutoff wave number, okay, cutoff frequency, and the guided distance. Fine. Yes, the last one is the wave impedance. So the wave impedance Z, Tm and Mn is equal beta eta over k, and yes, we may expand like this in terms of the cutoff frequency only over f to the whole square. Fine. So wave impedance definitely is a proportional to the eta, intrinsic impedance, as well as the cutoff frequency. Fine. Now some of the points actually I would like to conclude here for both, for the TE1 TM mode. So how we can summarize all those things? Okay, so let me write something and then we can discuss. This is for TEMN mode. Okay, n is 0, 1, 2, these things, and m is 0, 1, 2, and so on. Fine. And definitely m is equal n is not equal to 0. For Tm and case, n is equal 1, 2, 3, and m is equal 1, 2, 3, and the cutoff frequency for both the case, okay, for the TE and TM mode are defined by the previous equation. Okay, these things, the cutoff frequency, this formula, remember? Okay, so this is the cutoff frequency. Now if you see, according to the cutoff frequency, okay, this formula, the cutoff frequency for both the modes, for the TE and the TM, for TE actually, particularly let us see the TE 10 and TE 01. Okay, these two modes. Okay, so these two modes basically less than the lowest order TM mode, which is TM11. Okay, 1, 1, TM11. So the lowest order mode here is for the TM case TM11. Okay, and for the TE mode, it may be the TE10 or TE01, depending upon the dimension how you are choosing. A is greater than B or B is greater than A. Okay, depending upon that the mode will come. So the cutoff frequency for this, okay, means for the TE mode will always less than this TM11 mode. Fine. Another point is that for A is greater than B, okay, for the rectangular waveguide, this TE10 mode has the lowest cutoff frequency. Okay, lowest cutoff frequency. Please remember these things when you are defining this dominant mode, TE10 mode. So this should be satisfy A is greater than B. Means I am saying here this is A and this is B, like this. Fine. Okay, and that is why we are calling as a dominant mode. Dominant mode. Another very interesting fact here is that this TE10 and TE01 mode, okay, these two modes are the degenerate mode. Degenerate modes. Okay, for what? For this is actually for the square waveguide. The square waveguide means A is equal B. Fine. So in that case, this will be the degenerate mode and the frequency will be same. Fine. Okay. And the last point is that if the waveguide is operating at the frequencies, okay, where more than one mode propagates, okay, so it is called as the overmoded. Fine. So this is all about the T and TM mode for the rectangular waveguide. So we saw also the practical aspect, and yes, in a lab scenario how we can measure all those things, lambda g and all these things. So there is a microwave bench. Okay, so I have prepared a separate that video lecture on it. Okay, if you interested I can share. So you can see how we can measure this, all the lambda g impedance and all the cutoff frequencies, and how to measure the frequencies. Okay, with the help of this microwave bench. Okay, so this is all about for this class. In the next class we'll see the cylindrical waveguides. Fine. So this is another very interesting topic. Okay, and these are the very two conventional geometries of the waveguide. Okay, we are utilizing in different applications in a domestic as well as in a military. Okay, in a defense also you will see this waveguide system, because this waveguide are capable to carry the huge amount of power at the large frequency. So still these rectangular and cylindrical waveguides are very famous, acceptable, okay, in a defense things. So yes, with this I'm finishing this, and we'll start once again in the next class the cylindrical waveguide system, followed by we'll be closing these things at the resonator. Okay, the cavity resonator. Okay, thank you so much.